Torvald Mårtensson. I work with testing and test environments for the Gripen fighter aircraft. I also work with, perhaps you've seen something on the news about the next fighter system that we started to work with. I also have this role called Technical Fellow, so that due to this I also am Associate Professor at Linköping University and also do some other stuff. So if you're interested in like master thesis, bachelor thesis, etc., or generally interested in Saab, please talk to me afterwards. I currently have this spring, I think it's 9 master or bachelor thesis students that I handle at Saab. So that's not at university, but at Saab. So yeah, it's something that we of course could talk about. Yeah. So what is then the takeaways from this talk? We'll talk about generally how do we test the Gripen fighter aircraft. Now Erik has talked about generally how we test software components. Now we'll talk more about generally how do we test the Gripen fighter. And of course, how is this related to software testing, which is more or less what we want to talk about here today. And I'll also give you 3 more specific examples of practices that we use every day, every week, when we work with development of the Gripen fighter. So not just theories, it's more about 3 more specific things. So the Gripen fighter, or the Gripen E fighter, is, as you see, an aircraft with more or less the same shape as the Gripen C and D versions. And these are the single and the dual seater that is currently operational in Sweden, Czech Republic, Hungary, Thailand and South Africa. And you might think that, well, it looks more or less the same, so what's the difference really? And the answer is that more or less if you look inside the aircraft, everything is either new or heavily modified compared to the previous versions of the aircraft. So for example, the fuel system, it's based on the system in Gripen C and D, but it's heavily modified to this new version, etc. And another big difference is that the level of integration between the subsystems in the aircraft is also much higher. So for example, how much data or how much information is transmitted from the HMI system to the decision support system to the radar system, etc., to the navigation system. It's much more interaction between the subsystems. And that also goes for the training system and some support systems. So a lot more data. So when it comes to testing of this kind of product, the challenges is related to large scale, to scale of the system, and that is both lines of codes, a number of components, so a number of hardware and software components, but also the scale of the development organization. So it's a lot of engineers that needs to talk to each other, and also it's more development teams that needs to interact with each other. The other factor that it's to a large extent the limiting how you work with testing of such a system is complexity. And here we mean connections between the subsystems, so connections between the software components and between software and hardware. So it's a lot more connections between different modules or components. So when it comes to testing, it's very much about how do you test a large-scale and complex software system, and it's about why is this then about software? And that is due to from the beginning of the Gripen project, from the first versions that we started with development during the 1980s. Already then, there was a strategy that as much functionality as possible should be implemented in software, and that's still also the strategy. So of course we do a lot of other types of testing of the hardware, etc., aerodynamics, everything. But to a large extent, if you look to what is the challenge when it comes to testing of the Gripen fighter, it's very much how do you test a large-scale and complex software system. So how do we do that? Well, the first principle or strategy you need to talk about is how to test on different levels. And this is, of course, not something new. If you look into one of the first books on software testing from the 1980s, this is one of the first principles that they talked about. Of course, you start with testing on a component level, where you test algorithms, precision, and range. Then you move on to a subsystem, where it's about the system functions in that particular subsystem, here illustrated by the radar. And it's also about the integration of the software and hardware. And finally, then you want to test the complete product, which is here the fighter aircraft with its support systems. So it's about the integration of the subsystems, it's about the system functions in the complete product and its operational capabilities. And the difficult thing is not to understand that we test on different levels, it's about to actually stick to that strategy, to actually test algorithms and precision, etc. on the component. Because what we tend to talk about is this strategy to shift left to test early, but when you're behind schedule, it's very tempting to start saying that, well, let's check that, we'll see that on the subsystem level, right? And we'll see that when we test the complete product. So it's tempting to not stick to the strategy. So that's more or less the challenge. Then it's about how we then test, how we combine different test techniques, which is then here illustrated by the agile testing quadrants. And this is from I think it's quite good illustration of how you need to combine different test techniques. And it's from this, for example, from this book from Lisa Crispin and Janet Gregory called Agile Testing. So what this means is that you need different test techniques for different purposes. And here to the left, you have test activities supporting the team, which is testing in parallel with development, which is different compared to when you test the complete system to critique the product. And you also have here at the bottom test techniques, which is then for when you look under the hood, so to say, for the product, which is different compared to testing the functions, isolated functions, and operational capabilities, scenarios, etc., for the complete product. And what's the challenge then? Then it's of course how to, in a good way, combine those different test techniques so that you have the right balance for the product that you're building and the ways of working in your project or in your organization. Then it comes to testing in different types of test environments, and we have different types of test environments. Here up to the left you see what we call software in the loop simulator. And that means that instead of testing your software with the real fuel system or the real radar or whatever your function is about, then you have a model that is then a representation of that system. So it could be a representation of the fuel system. So when you want to monitor or control the fuel system, instead of having the response from the real fuel system, you have a piece of software that is working in the same way, providing the same response. So you have then a model of the fuel system, a model of the radar, model of the engine, etc. And also models of the surrounding world, of the tactical environment, so you can interact with other aircraft or things on the ground, etc. And here everything is then software. So you have the same software that is actually in the aircraft, but then everything in the test environment is then synthetics. We also have these combinations of where we have simulation and you have real hardware, which that we call hardware in the loop subsystem rigs. And there, for example, if you want to test the fuel system, then you have a test environment with the real pipes and the tanks. But other systems, for example the radar, you're not really interested in that, so that could be a simplified model. And in another test environment, you want to test the radar, and then the radar is real, the computer that is working with the radar, controlling and monitoring the radar is real, and then that's the real hardware. But you're not so interested in the fuel system, so then that could be a model. So we have different hardware in the loop subsystem rigs for different purposes. Then we have hardware in the loop system rigs, where as much as possible is real hardware. So why is then not everything hardware? Well, for example, if you have like the GPS system, then you have a real GPS and you fly away in the simulation, then the GPS will say that you're right on the same spot, right? So then you want a model of that, so the simulation works correctly. And then finally, of course, you have the test aircraft. So a lot of testing that we do is also, of course, in the test aircraft. And that is due to that some things, for example, when it's about data links, the electronic warfare system, radar, etc., then it's very difficult to produce accurate models. So then you need to test in the real their product. And so therefore there are a test aircraft that is placed on here at Saab in Linköping. So there we have the flight test department that is then responsible for maintaining and operating those test aircraft. So in the second part of the presentation I will then talk about 3 more specific things that we use like every day, every week. And that will be a simulator on every developer's desk, nightly automated testing in the rigs, and exploratory testing of the complete system. And we talked about this, as we said, the software in the loop simulator. And we call that MySim, so it's My Simulator basically. And that is then that everything, every model of every physical system is then a model. So it's, as we said, a model of the engine, of the fuel system, etc. Every sensor is also a model, so the IR sensor, the radar, etc. And also we have this model of the tactical environment with targets and threats. So you have the same software as in the real aircraft, executing not on the real bespoke hardware, but instead executing on a standard Linux computer, interacting with all the systems, but represented by software. And due to this, then the developers can log on to this from their own desk. They don't have to leave their workstation where they work in their office. And they don't need to book anything, don't need to go to a special test facility. So due to this, that you have this availability, you can then make changes to the software, make a new system build, and see how it works, and without any effort to book or to go to another place, etc. So due to this, the developers are then more confident that their software is working, not just their software module, that it works in the complete aircraft. We also use MySim for automated regression testing to test on different levels in the product, which also is a good way to provide faster feedback to the developers also when it comes to regression testing. So the second thing I wanted to talk about was nightly automated tests in the rigs. And that's something different. We talked about a virtual environment before, so everything was software. Here it's about testing on the same hardware, on the same computers, and as much hardware as possible as in the real test aircraft. So what we do is that we test the latest system build. We test that nightly to see that, well, we do a fully automated startup, takeoff, we maneuvering with the aircraft, and then landing, and also using some of the functions. And due to this, we can see then that the system build, that we have stability and integrity on real hardware. So we can also test like the real-time aspects, etc., things that you can only see on the real hardware, not in a simulated environment. It's also a good way of handling when you have those really naughty problems that are really important, but they only occur sometimes. So you have to rerun the same test many, many times. So we had situations when we have rerun the same test like 1,000 times in order to see what is the problem here. And so you then create an instrumented build, which is then just looking for the problem, and then you can find then data from when that problem finally occurs. So it's also a good way to work with these kind of problems, these nightly automated tests in rigs. So finally, I'd like to talk about exploratory testing on the complete system. And exploratory testing, that means that instead of working with like test cases that you have like a step-by-step instruction for what the tester should do. Instead, you provide a more open task for the engineer that works with testing. And we practice this in virtual test teams, where we have then experienced engineers coming from the different development teams that then work together in a virtual test team and test on a weekly basis, and then test together with a real flight test pilot. So you go to one of the system rigs where the flight test pilot is then sitting in a cockpit that is with the same displays and etc., and then have this visual environment where you can fly more or less like in the real aircraft. And then the test team is then in the room next door. And all the equipment from the aircraft, the computers, etc., is then in this like a server hall in another room. So having these experienced engineers testing together with different representing the different test teams, we've seen that this is a good way to identify complex integration problems which are difficult to identify with automated testing, because you don't know what you're looking for. If you have an automated test case, then you write the test case checking for something. Here you more explore the product and then find the problems that you didn't know that you have. So we started working with this. It was about a year before the first flight of the first Gripen E test aircraft. And after that first year, I had the series of interviews of all these free test teams that we had in parallel on a weekly basis. And these are two quotes that I'd like to share with you. And the first here is an engineer saying that, well, we could test according to the ideas we had. We wanted to understand the system that we were building and to find the weaknesses in the system. And to me, that's pretty much what exploratory testing is about. The second quote is someone saying that the quality of the problem reports improves if there are people from different subsystems participating at the test. And that means that, well, instead of having this test department that sends a problem report that says it doesn't work, greetings from your tester, instead you have the people that actually is working in the development teams, that they are together testing the product and then can discuss what is then the root cause, because they contribute with different knowledge. So when the engineer goes back to his desk, then he has not just a vague description of the problem, he has almost the solution, or at least the root cause. So what we have here is that the developers from different development teams, they test together with an end user representative, so that's a flight test pilot, and they test the complete system, so not just a module or a subsystem. So with this, it's time for summary and takeaways. We talked about how we test generally the Gripen fighter, and we've seen that, well, it's very much about testing a large-scale and complex software system. And we talked about how do you do that. You test on different levels, you combine different test techniques, and you use different test environments. And we also talked about the challenges related to this. It is about how do you then stick to the strategy to test the right thing on the right level, find the right balance, and also how you then put the right test activity in the right test environment. We also talked about these three more specific things, free practices that we have benefits from every day, every week. And that was MySim, this simulator available from every developer's desk. We talked about automated testing in the rigs, so that means testing on the real hardware and why that is important. We also talked about exploratory testing of the complete system that we practice with these virtual test teams. And that concludes my talk. Are there any questions? Yeah?
Can I give you the microphone? Okay. Have to have the questions on the mic. So.
Yeah, please.
Yeah, thank you for your nice presentation.
Hmm?
I have a question regarding the deterministic part of a test.
Okay.
Because if you're in the flight test in the end product, you are essentially doing there may be real-time decisions by a test pilot, for example. Whereas in a simulator, it may be the case that you enter your test data and run through the entire test without having like a feedback loop of decisions. Is that a relevant
I'm not sure I
So
understand the question.
well,
What is, yeah,
So what I'm saying is that if you have a simulator
yeah,
and you want to run like a nightly test,
mm-hmm.
you will most likely enter your data
Mm-hmm.
and you run like an open loop test, which is deterministic through the entire time frame. That's my assumption.
Yeah, it's correct that what you do is that you start up the aircraft, you expect that I will, for example, have no alerts. And then if you have, like, say, some system says that, well, my startup check didn't pass, then it's a problem, right? So your assumption is that there will be no all startup check will pass, and so what you're checking for is that. And then, yeah, so it's different. If your question is that different compared to if you're having someone sitting in the cockpit and testing functions. Yes, there are two different types of tests. That is correct, and that fits in to these quadrants. So there are very different types that are for different purposes. Yes, yeah, and I'll be happy to talk more afterwards if you want to discuss more. Any other questions or yeah, please.
Yes, so I'm very curious. What is the big challenge up front? What is the most critical parts that one strives to find out?
Yeah, I would say that, well, we had one of the slides in the beginning said that, well, the challenges is about scale and complexity. And I will say that, well, what we talk about now is more that to scale up. So I mean, it's not about testing a system, it's about testing system of systems. And also when it comes to complexity, I mean, now we're into AI models that should provide more advanced decision support. And that is, I mean, what I would say that testing an AI-based system, it's very much about testing a very complex system. So I would say that these challenges, how do you test something large and how do you test something complex? I think that's the challenges, and we will see more of that. So, yeah.
Fantastic. And it perfectly makes sense due to the last or the first question I said when it comes to like the virtual twins and yeah. So thanks a lot for a great presentation, everyone.
Yeah, thanks. And I'd be happy to talk more if you want to follow up that. So yeah. Any other thoughts or ideas? Yeah.
So were there any bugs that were found after all the tests were passed? And if so, on which stage of testing that bug could have been found if we put more time on that stage testing more?
Yeah, so I'm not really sure. So let's see if I understand your question. So you want to say if all tests were passed, do we find anything after that? Yeah. So what do you mean? What kind of tests were passed? Do you mean like a test on component level or
all the level of tests were passed?
Yeah.
And then on the production, a bug was found.
Yeah. So okay. So generally, I would say that for every system, it's very difficult to say now we tested everything. So it doesn't matter if you test a fighter aircraft, if you test a nuclear power plant, or so you have this. You can always especially on the system level, you can always say now it's another time of the day. So now if we rerun the test, something is different. So of course, for any type of system, when you come into production, you find problems. So it's more a matter of how many problems do you found, and I mean, so it's of course that it's also something. If we look into the Gripen C and D versions, of course there are updates on the aircraft that is with, for example, the Swedish Air Force, that there are problems that are identified, and then if it's something really urgent, you do it fast. If it's not, if it's more of an improvement, you're not so. You don't need to do it that fast. Yeah. So do I understand your question or? Yeah. Okay. Yeah. Good. Okay. Anything else? Yeah. Please. Yeah.
There you go. So mine is maybe more funny stories side.
Yeah.
Because when you all talk about it, it sounds like you really have a good plan with all the testing process. How much trial and error have you gone through throughout the years, and you still are going through?
Yeah, I mean, I would say, as we said, on the 4 quadrants we talked about, and we said the left side was about testing in parallel with development. And that is generally, I would say, that's what I think you refer to with trial and error. Because when you build a very large and complex system, you don't really know what you're looking for. And it could also be that, well, starting with what the customer wants. I mean, we have another test facility that I didn't talk about here today, is that we invite flight test pilots from the air forces that are our customers, and we let them try out prototypes. And I mean, because we don't work really like, you know, well, Google saying, trying different things, and yeah, you can't do that. So you then have demonstrations, and then what do you think? Which is good and bad? So that's what you refer to, trial and error with the customer. And also when it comes to designing a system, you might think that, well, it's not just writing down what the system should do, but the problem is then, well, what does that really mean? And what does it mean if there's a failure in that system? So it's very much about, of course you need to work in a structured way, but very much it's about to explore what is the system that we want to build, what is it that we want to construct and implement here. Yeah. So very much of testing is about finding out what behavior are we looking for. Yeah, good. Yeah, I think it's 2 questions, so please.
And who wants to ask a question?
Yeah, well, I think there was another one there as well. Yeah, so.
Yeah, hello.
Yeah.
So we know that the Gripen E has a very good interoperability with a lot of different weapon systems. So,
yeah.
For example, I think it was one of the first fighters to fly the Meteor missile, I think.
So to the Meteor?
Yeah,
I think it wasn't the C version, right? So, but it was Gripen, but I think it was Gripen C that had the Meteor first. Yeah.
So a lot of these systems are designed in other countries, and yeah, when you have, for example, a new customer that wants to integrate their own weapon system,
yep.
These are where I see challenges come in when it comes to coming up with testing scenarios, for example. So what I'm trying to ask is, how would you come up with scenarios, or how would you test the entire system, the aircraft, when you're integrating something completely new, which wasn't even developed in-house by Saab, or for example, if it's a new system by another country, and would their engineers come to Saab and work on this, or how would you go about planning it? Basically.
Very different depending on what's the situation and how complete is the product that you're integrating. So I mean, it could be as this is what it is, integrate it. It's an established system that's working with other aircraft, or it could be that, well, this product is the subcontractor is we are working with it together. And then they, as you say, they do testing at their facility, but they also come and we test together. So yeah, so both.
Okay, yeah, that's my question. Thank you.
Yeah, okay, thanks. So let's talk more afterwards if you want to. Yeah.
Who else was next?
Yeah.
Amazing. Yeah, funny thing that you mentioned Google. I used to work a lot with them the past month, and I mean, when it comes to Linköping as a city, supercomputers are getting more popular. We're doing even quantum computing, and when it comes to Linköping as a region, really, setting a lot on making this like the computer center. And speaking of complexity and testing of systems, how is the collaboration there? Is it something
with Google or?
Oh, sorry, with Linköping's supercomputer and supercomputers and pretty much quantum quantum computing in general.
I'm not really into that. Perhaps one of my colleagues could fill in, but I mean it's an ongoing collaboration with this as I said, the supercomputer center. But I'm not really what kind of projects and what's the setup. So
Cool.
Yeah, good.